So this is part 2 of our introduction to calculus for the purpose of AP Physics C. I'll be talking briefly about integrals and what they are and how to calculate them. And the structure will be fairly similar to what we did for derivatives. Although one departure from the way we talk about derivatives in talking about integrals is that there are actually two types of integrals, or two ways that we use the word integral. An indefinite integral is the first type, and a synonym for indefinite integral is antiderivative. And it's actually a concept that we need mathematically, but we actually don't end up solving many indefinite integral problems in physics. It's just a necessary skill for solving the second type of integral, which is called a definite integral. So here we go. If I write this sort of elongated long s, and then f of x, and then a dx there, the way that I would read this is the indefinite integral of f of x. And if I were to put a question mark there, then what I've written here by hand in black is basically a question that's asking what function has a derivative of f. It's an antiderivative. Instead of taking the derivative of f, we're asking what function, when we take its derivative, has an answer of f of x. So just for example, if I write integral sine x cubed dx, the integral of x cubed dx, what function has a derivative of x cubed? Well, maybe think about it. X to the fourth over 4 has a derivative of x cubed. Because if you imagine taking the derivative of this function, the 4 comes down, cancels with that 4, just leaving x, and then you decrement the 4 in the exponent, leaving a 3. There's actually another function that, if you think about it, would also have a derivative of x cubed, and it's x to the fourth plus 1, because the derivative of this constant 1 is 0, so the derivative of this function is x cubed. And come to think of it, no matter what constant we add to x to the fourth over 4, the derivative of that function would be x cubed. So x to the fourth over 4 minus pi, or I guess in general, the antiderivative of x cubed dx, the antiderivative of x cubed, or the indefinite integral of x cubed dx, and don't even worry about what the dx is doing right there. You might just think of it as a piece of notation for right now. The antiderivative of x cubed is x to the fourth over 4 plus c, and c is a constant of integration. So actually, this is a way of writing the idea that there are infinitely many different functions whose derivative is x cubed over 3. Okay, let's do another example. What's the integral of x squared minus 1 dx? Well, if you think about it, x cubed over 3, when you take its derivative, will give x squared, minus x, when you take its derivative, will give minus 1, and then plus any constant. This is a way of writing an infinite number of functions that all have a derivative of x squared minus 1. The integral of 1 dx, what function will have a derivative of 1? X plus c. I guess when I am writing this and I put the letter x there, I'm telling you that the function will be a function of x. If I write this antiderivative and I put a t there, I'm telling you that that we will be having a function of t. So what function of t has a derivative of what? Well, you can see that the number 1 is sort of tacitly there as the coefficient of that dt. So what function of t has a derivative of 1? Well, t plus a constant. Those are some more examples of indefinite integrals problems. As with derivatives, constants come out of integrals, so the integral of some constant times f of x dx is equal to the constant times the integral of f of x dx, for instance. If I want to find the integral of 5x dx, I can do that by finding 5 times the integral of x dx, and the integral of x dx is x squared over 2, so 5x squared over 2 plus c. Should I have written 5c? Well, 5 times a constant is a constant, so I can just write a constant there and be fine. Okay, well, how about this mess? Well, the integral of 2 kilogram meter per second squared dt. Well, if you remember from our derivatives presentation, constants are just, units are just examples of constants. They're just examples of coefficients. So they come out of the integral just like everything else does, or just like all the other constants do. Here, the number 2. 2 kilogram meters per second squared times the integral of dt. Well, the integral of dt is just t plus c. And finally, what function of y has a derivative of mg? mgy plus c. Cool. As with derivatives, if you are taking the integral of a sum of functions, it's the same as the sum of the integrals of the functions. So the integral of f plus g is equal to the integral of f plus the integral of g. So, for example, if I'm taking the integral of x plus 5 dx, I could do this all in one go and say, what one function of x has this derivative? But I could also think of it like this. I could say, what function of x has a derivative of x, and what function of x has a derivative of 5. And so here, the integral of x dx is equal to x squared over 2 plus a constant, and the integral of 5 dx is equal to 5x plus a constant. But a constant plus a constant is just a constant, and so this is an example. This is actually all of the infinitely many functions whose derivative is x plus 5. So what have we been doing? We've been talking about indefinite integrals, which is just the same as an antiderivative. This will sound like a little bit of a departure, but I'd like to return to the idea of the area of a graph. And if you recall, in our physics presentation so far, we've been looking at the area of the velocity as a function of time graph and saying that it relates to the displacement of an object with that velocity. And we also said that the area, the integral of an acceleration time graph, tells the change in velocity of an object. And so how does that integral, which relates to graph area, relate to the way I was just using integral to mean antiderivative? I'll tell you. But let's refresh our memory about what's going on with graph area. If I give this as a given of the problem, a constant velocity of 5 meters per second, I could ask, what is the displacement of this object between 1 second and 4 seconds? Algebraically, I can use our constant velocity equation, because the velocity is in fact constant. Delta x is v delta t. Let's see, and v is 5 meters per second, and delta t here is 3 elapsed seconds, so 15 meters. And I'd like to show you that the graphical analog, again, of that is the area of this red rectangle, which has a base of 3 seconds and a height of 5 meters per second. So over an interval, the integral of the vertical variable, in this case velocity, with respect to the horizontal variable, in this case time, graphically is kind of like the area between the function and the horizontal axis. Conceptually, this area, this integral, represents the sort of accumulated effect of what's on the vertical axis over the interval of what's on the horizontal axis. That is to say, if you think of displacement, a change in position, being the effect of having a velocity, then the accumulated effect of having that velocity between t equals 1 and t equals 4 seconds is a displacement of 15 meters. The accumulated effect of this property on the vertical axis is this area. the area between this function and the horizontal axis. So in this different situation, we have a changing velocity as a function of time, and I could ask this question: what is the displacement of this object between t equals 0 and t equals 4 seconds? Well, again, I would use my geometry skills to find the integral. The integral of velocity is displacement. And what is the area of this red rectangle? Well, it's 1/2 base times height, and the base is 4 seconds, and the height is 3 meters per second. And so that will be an area, a displacement, an integral of 6 meters. Recall that area that is below the horizontal axis sort of counts as a negative area. So if I use the same function, this thing that has a changing velocity, it looks like it has sort of a forward slowing down velocity between t equals 0 and t equals 4 seconds, and a backward velocity in the negative direction, speeding up velocity between 4 and 8 seconds. This area down here counts as negative. If you like, the height of this triangle is negative 3 meters per second. So this red area represents a displacement of 6 meters. This red area represents a displacement of minus 6 meters for a net displacement of 0. I'll try and act out this motion with this as the positive direction. Something has an initially large positive velocity, then slows down, and then has a speeding up negative velocity and returns to where it started. It has 0 displacement. Okay. Still without fully connecting with the idea of definite integrals, which we talked about, the idea of indefinite integrals, which we talked about in the first few slides, I'd like to talk a little bit about why we write our expression for integrals the way that we do. If you recall, when I talked about derivatives, I ended up saying that if you take the limit of secant segments, delta x over delta t, or delta vertical axis over delta horizontal axis, then that becomes closer and closer to approximating the slope of a tangent line. And that's why we write dx dt to mean the derivative of x with respect to time. I'm going to say a similar line of thought that explains why we write integrals the way that we do. If you recall, I had said during that last presentation that when something is teensy, when we take the limit of something as it approaches 0, so it's just ever so teensy tiny, infinitesimal, then instead of using delta, we use the English letter d. So if we have this sort of curvy velocity as a function of time, then let's check this out. During a teensy time interval dt, you can see that the velocity doesn't change very much during that tiny time interval. And there's a teensy displacement, delta x, represented by that red rectangle. If we approximate that the velocity is approximately constant during this time interval, then it is indeed a rectangle as opposed to a trapezoid or anything like that. That is this red region. And the red region represents the teensy displacement, and the area of this teensy rectangle, based on the approximation that we've taken a small enough elapsed time that the velocity doesn't change at all. It's an approximation, but it's a fair approximation as you take the limit as delta t goes to 0. During this teensy time interval, there's a teensy displacement, dx, and the value of it is dt, the base of the rectangle, times v, the instantaneous value of this velocity. If you take a whole time interval that isn't teensy, between some time t1 and some time 2, then you can imagine accumulating some displacement as being like having a lot of teensy rectangles, each of which represents a teensy displacement. And so this whole red area, this whole red region, the accumulated displacement between t equals t1 and t equals t2, it's like the sum of all of these rectangles. So if I just start with this line of math, then I can just add a squiggle sign that means add up all the little infinitesimal bits. That's what that little squiggle sign means. It just means add them all up. The sum of all the dx's between t1 and t2 is the sum of all the v dt's between t1 and t2. Well, let's look at the left side of this equation, which just came from the previous line. If you add up all the infinitesimal displacements dx, you get the whole displacement, delta x, between t1 and t2. Add up all the teensy bits, you get the whole displacement. So just replacing this line or substituting it into this line, the displacement, delta x, between t1 and t2 is equal to squiggle sign t1 to t2, that is to say, the integral from t1 to t2 of v, which is a function of time, v of t, times dt. This statement is saying that displacement is the integral of velocity between two time moments over an interval. So reading this, the integral of v of t dt means the idea of finding sort of the area between this function on the vertical axis and this horizontal axis. T is on the horizontal axis, so we have dt to indicate that the thing is on the horizontal axis when we're finding the area of it. And now I believe I've kind of explained where this kind of notation comes from. Like, what was the deal with dx here? Well, at the time I said, well, just consider it some notation to say what we're taking the antiderivative with respect to. But now I think I've illustrated that this dt actually gets inherited from the idea of teensy rectangles. So if I were to read this line, I would say the integral of velocity as t goes from 0 to 2. Just as displacement, change in position, is the time integral of velocity, the time integral of acceleration between a time interval t1 to t2 is equal to the change in velocity. That's the calculus way to write that statement. Okay. So now that I've done this, you can see that a difference between this line and this line here is that here when I was talking about indefinite integrals, antiderivatives, there were no numbers here. There were no what's called limits of integration. But here there were limits of integration. So a definite integral is the other kind of integral. We talked about indefinite integrals, which just means the antiderivative. And now we're talking about definite integrals, the second kind of integral, which relates to finding the area between some function and the horizontal axis over some interval. So if it is a given of this problem that the velocity as a function of time is equal to the square of the time, and of course the units don't work there, but we'll just play fast and loose on the units. Can we calculate the displacement between t equals 0 and t equals 2? Can we find the integral between 0 and 2 of t squared dt? Yes, here's how to do it. And I'm going to state this without proof. You'll prove in your calculus class that this is the way to do this task. The first thing you do to calculate the value of a definite integral, to find this area over an interval, is to take the antiderivative of the function that's to be integrated. Take the antiderivative of what's called the integrand. You don't need to worry about putting a plus c, and you'll write that it is, you'll take the limits of integration and you'll write that you should evaluate the function between the limits of integration. So what did I do going from here to here? The antiderivative of t squared is t cubed over 3. I'm omitting the c, the plus c. And then, instead of a squiggle on the left side with a 0 and a 2, I'm going to put a straight vertical line with a 0 and a 2. This means, and so the way that I would read this line is t cubed over 3 evaluated between 0 and 2. Then, the way that I perform this evaluation mathematically is to take this expression and substitute the number on top, and then subtract what I get when I take the expression and substitute the number on the bottom. So t cubed over 3 evaluated between 0 and 2 is 2 cubed over 3 minus 0 cubed over 3. That's 8 over 3. And again, I'm not explaining why this is the case. That's for a calculus class. If this feels uncomfortable, you'll gain it within the context of this class, probably not by understanding where it comes from, but by practicing multiple examples until you see that you do understand and can repeat it. And that's a fine way to learn stuff too. All right, so the displacement of this, the area of this velocity time curve between t equals 0 and t equals 2 is 2.67 meters. Hey, that's really cool. We just found out the area under that curvy function using this new skill that I have presented. Let's do it some more. Remember that the area under the horizontal axis, this area, will end up counting as negative. If this is just a y as a function of x mathematically, if y equals x squared minus 4x plus 2, if that's the given of the problem, I might ask, what is the integral of this function between y equals 0 there and y equals 4 there? And again, the dx here just means the function on the horizontal axis of this graph is, the variable on the horizontal axis of this graph is x. Alrighty, so when I take this integral, the integral of x squared minus 4x plus 2 is, let's see, what function has a derivative of this? Let's take the antiderivative of the thing being integrated. X cubed over 3 minus 2x squared, that's what has a derivative of 4x, plus 2x. And we're going to evaluate that between 0 and 4. And let's see, that's 4 cubed over 3. I'm going to substitute the 4 in. 4 cubed over 3 minus 2 times 4 squared plus 2 times 4. Why didn't I write minus 0 cubed over 3 minus 2 times 0 squared plus 2 times 0? I could have, but I happen to see already as I write this line that those terms would all end up being equal to 0. So I'm just not going to bother writing it out. So this value of this integral ends up being minus 2 and 2/3. What that means is that the total integral that's shaded here in red has a net negative value. These pieces contribute some positive value to the integral between 0 and 4. But this is negative enough that the total net red integral is negative. So let's just do some more examples of definite integrals, of finding areas over an interval. What's the integral of x squared minus 1 dx from minus 2 to minus 4? Well, take the antiderivative of this function, x cubed over 3 minus x, evaluated between negative 2 and 4. I perform the evaluation by substituting the top number and then subtracting what I get when I substitute the bottom number. And you can confirm for yourself that the answer is 18. All right, what's the integral of dx evaluated between 2 and 4? Well, really, this is the function 1 dx, and its antiderivative is the antiderivative of 1 is the function x. So x evaluated between 2 and 4 is, let's see, what happens when I substitute 4 for x? 4. Minus what happens when I substitute 2 for x? 2. 4 minus 2 is 2. if I do the same problem but with dt, it just means that I'm imagining the area of the function 1, imagining basically the area of this function with t on the horizontal axis. What is the area of this function between t equals 2 and t equals 4? Well, I can already tell that it's going to be a rectangle with area 2, and let's see if math can confirm that. Okay, the function of t that has a derivative of 1 is t, just like the function of x that had a derivative of 1 was x. And t evaluated between 2 and 4 is 4 minus 2, that's 2. Great. What function of y has a value of what function of y has a derivative of mg when m and g are constants? Well, m and g come out of the integral, leaving the integral of 1 dy. The integral of mg dy is mgy. Evaluate that between 0 and h. Substitute h for the y, and you get mg times h, minus what happens when you substitute 0 for the y. Mg times 0 is 0, so I'm not going to write that term, mgh. This makes me feel much more comfortable, actually. We've been doing all of these problems in a way that a physics teacher might just say is wrong because the units don't work. But here's one where the units are here and the units will work. If the velocity as a function of time of some object is 5 meters per second cubed times t squared minus 2 meters per second squared times t, then what is the displacement between t equals 0 and t equals 1 second? Well, why are these units good again? Well, if the left-hand side needs to be measured in meters per second, and it does because it's a velocity, then this term has to be, this first term in this sum has to have units of meters per second needs to have units of meters per second. And t is going to be some number of seconds. So yeah, some number of seconds. That squared will cancel with 2 of these seconds in the denominator, leaving units of meters per second there. And if I substitute t as some number of seconds here, that seconds will cancel with 1 of the seconds in this denominator, leaving units of meters per second there too. So that's why this is a properly formatted question, and now let's work on answering it. The displacement is the integral of the velocity with respect to time between 0 and 1 second. There I've substituted the expression for the velocity. Let's see. When I do this integration, 5 and meters and seconds are all constants. They don't get integrated. They come out of the integral. And so 5 meters per second cubed just passes straight down, and the integral of t squared is t cubed over 3. Okay, minus, there's our 2 meters per second squared, and the integral of t is t squared over 2. Evaluate that between 0 and 1 second. Why don't I need seconds there? It's because 0 seconds is 0 meters, is the number 0, is 0 hippopotamuses. They're all just 0. And so now, when I substitute 1 second there, that's what that looks like. I haven't written out what happens when I substitute 0 because I know that all of these terms will just become 0 when t equals 0. And so yeah, 5/3 meters minus 1 meter is 2/3 of a meter. And the units work just like I needed them to. You could repeat the same problem dropping the units and just adding the units later. Here's what that would look like. The integral of this function is this function, and when I substitute the number 1 for t, or when I evaluate between 0 and 1, then here's the result, and I can just tack on meters there, because I know the displacement has to be measured in meters.